Hello, everyone. It's my pleasure to introduce Shmuel Weinberger, who will be telling us about the persistent homology and the geometry of function spaces.
All right, thank you. Yeah, I mean, so it's a real pleasure to, well, it's a bigger pleasure to see this activity taking place because quantitative topology and applied topology are two subjects that are close to my heart and have, I mean, they both have multiple motivations, but in particular, they have common motivation. And I think the subjects are deeply linked, although at the moment it might be more in philosophy than day-to-day practice. Although, you know, it's a little bit hard to be so specific. In any case, what I want to talk about is I was going to make the title just PH of X to the Y. I thought it would be really cool to be entirely symbols, but then I thought that was too geeky. So what I want to talk about is persistent homology of function spaces. Okay, and I will, you know, I probably, you know, let me break the news to you. I don't know the answer. Okay. Firstly, the ordinary homology of function spaces is a very central thing that's studied in algebraic topology. Most commonly, the loop space, where you get information about homotopy groups. At least one point of view is that you just keep on iterating, taking loop spaces and then computing their homology. That was the point of view in Sarah's thesis. So computing ordinary homology of function spaces is a central deal, right? What we call homotopy is H of maps is H0 of function spaces. Okay, so asking about persistent homology, well, there has to be a functional. We'll talk about that in a little bit. That's obviously some refinement. The infinite length bars are the classically studied homology. And I hopefully will entice people to try to think about to what extent can we understand the persistent homology of function spaces. I won't tell you everything we know, but I'll explain some ideas. And if you like, ordinary homology is about the homotopy type of function spaces, right? So persistent homology really begins exploring the function spaces themselves and trying to understand what kind of geometric properties they have. Okay, so that part is a little bit aspirational, but hopefully I'll give some examples. Okay, so let me start off with some background, which is sort of a little bit about how I adjusted from quantitative topology to just give some examples of non-quantitative theorems that I've liked at some point in my life. Okay, so this one, so if I have a map from an n sphere to an n manifold, okay, so I didn't give m a dimension, so let me give one now. Okay, so that's supposed to be a closed n manifold. We'll imagine that it's a PL manifold, and suppose I have a degree 1 map. Then there's a statement that something combinatorial follows from it, which is that you could subdivide the sphere, okay, and you could subdivide, which I think of as the boundary of the simplex, if you like. Okay, and I could subdivide M, it's a triangulated object. Okay, and then after the suitable subdivisions of both, then you could find a combinatorial isomorphism between them. Okay, so do people recognize this theorem? Oh, if you could interrupt me, I'm going to ask, and I hope that somebody or other answers. Do people recognize this theorem? Okay, it's the Poincare conjecture. Okay, if you have a degree, okay, you need to have a homotopy equivalence between manifolds. Okay, so it's a little exercise in algebraic topology about, you know, that if you just had a degree 1 map from a sphere, it's automatically a homotopy equivalence. So first you prove that M is simply connected, and then you go ahead and use Poincare duality to show that M is a homology sphere, and so on and so forth. Okay, so this is the data that it takes. And you now might ask, suppose I take a manifold, which is a PL manifold. I have isomorphisms with little local charts to balls. Okay, right. So I mean, I have complete testimony that it's, that it's a PL manifold. Okay, and Now I'd like to know how many subdivisions do I need to do, right? How hard is this amazing theorem, right? With whose history I won't tell you, right? But in dimension 5 and higher, it's older than I think most of the audience, okay? And, you know, the question is, how many subdivisions do you need in order to get this isomorphic? So the answer is we don't know, okay? That's the, if I reversed it, if suppose I made the math from, instead of being from Sn to Mn, suppose I would have reversed it and I would have made the math from M to S, and that I'd have that map and it's a homotopy equivalence, okay? So in fact, any manifold has a degree 1 map to the sphere, and if the manifold is a homotopy sphere, that degree 1 map is a homotopy equivalence, so that's not so much data at all, okay? Now you ask how many subdivisions you need. In terms of that, it turns out to not be a recursive function of the number of simplices, okay? Completely wild, okay? You can't give a bound like 2 to the 2 to the 2 to the 2 to the number of simplices. On the other hand, when you reverse the arrow, so by the way, so it's the same theorem, but there are 2 different quantitative versions of the question, something that happens a lot, that things that are mathematically equivalent when you do the quantitative form, you get different questions that have different subtleties. So that one, so the version where you go from M to the sphere has a non-recursive bound. It's like the busy beaver function for people who are into that kind of thing. On the other hand, in this direction, we know it's a computable function, but we know almost nothing else at all about it, okay? It's a very fundamental question. If you like, it's the question of understanding the Poincare conjecture as opposed to following the proof line by line, okay? You know, I mean, and that's where my love of quantitative topology comes from, because there are all sorts of things that we prove indirectly by some means, and that we, you know, and at the end, we don't understand the theorem, okay? And so if you're a practical person, I think because you want to generalize them and therefore you want to understand them better, but if you're an impractical person like me, you just want to understand the things you know, okay? So the Poincare conjecture is something we know, but I would submit that from some point of view, we don't really understand, okay? At least my point of view today. Here's another theorem that's even older. It's a theorem of Reine Thom. If you take a closed smooth manifold, and now you think of its tangent bundle, so at each point of the manifold, there's a tangent plane. You think about the manifold, therefore, it's giving you a varying family of planes. So it defines for you a cycle in the homology of the Grassmannian. And Reine Thom theorem says that your manifold is the boundary of some manifold 1 dimension higher, if and only if that homology class is 0. Okay? Okay, so now the question would be, do you understand, you know, if I'm given a manifold and I could bound its complexity in some fashion, okay, like the number of simplices, so you can imagine using some kind of volume notion, okay? The question is, can you bound the complexity of the thing that it bounds, okay? So this was a question asked by Gromov in the 1970s, and at that point, he sketched a proof that gave a bound that was a tower of exponentials, where the size of the tower was like 2 to the 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 number of simplices, or to the volume, and the number of 2's was like dimension -2, okay? Nowadays we know a lot better about that. We know d to the 1 plus epsilon, right? So you could get a lower than, not quite linear, which was Gromov's bold conjecture from the 1970s, but you could do, you know, any power of the number of simplices larger than 1. So you can be a judge, okay, and that's a theorem that I want to explain during this talk, or at least explain one of the main pieces of. And unfortunately, at the end of the proof, you might say, well, we've learned something new, but it might not be really insight into the coordinate problem. Okay, another problem, which is if you have any decent n-dimensional anything, say polyhedron, doesn't have to be a manifold, and it could actually be, you know, suitable metric spaces. They all can be embedded in Euclidean space of high enough dimension. Sometimes you could do it lower, okay? So, but then you could do it in higher, right? Let's say that's the Whitney embedding theorem, okay? And then some other, might be a few other people in purely topological settings. But there are other questions that you could know. You could ask, how distorted is the embedding, okay? And now versions of this are, kind of very important in algorithms. Frequently, X will be, say, a point cloud or something of that sort, and that one will want to either do dimension reduction. What I believe is, although I don't know of examples of this, well, after I say that, I think I do know some examples of this, where you might actually do the reverse. You might choose to do dimension inflation rather than reduction in order to improve the distortion. Okay, I know people might not be consciously doing that in some of what they do, but I suspect that people are. Okay, so now I'm blathering. Henry, edit all this stuff out. Okay, afterwards. Okay, there's no reason for this to be an honest record. So in all cases, we don't know the full answers to these questions. I don't know, the growth of the first function. We found that distortion. There are things that are known, like there's Bourgain field that distortions of metric spaces, if you embed them in Hilbert space. When you wanted to put it down to a particular Euclidean space, there are general theorems in the two sets that cover about half the dimension. Anyway, and then when you go below the dimension, sometimes you even move to undecidability. This is a very rich area. Okay, so I'm going to focus mainly on the middle one because the middle one turns out to be closest to the theme of persistent homology of function spaces. Okay, but for people who are familiar with high dimensional topology, right, like Whitney embedding is really the statement that any function can be approximated by an embedding. So, there really is a function space hidden in embedding theory. And I think in Florian's talk yesterday, we talked about how there are more subtle function spaces than you think of at first glance, like configuration spaces of the things you're trying to embed. So there are things about the geometry of the map that should be reflecting the geometry or the analysis of the map should be reflecting the geometry of the situations that you are being related to. So now let me give a little bit more background. So this is my picture of persistent homology. I believe that anyone who got up this early in the morning to hear a talk that starts with PH knows what persistent homology is and probably knows the stability theorem. Okay, so I decided that I will not explain that. Okay, so let me give you a drop of more background to convince you that persistent homology of function spaces carries geometry that everybody has cared about their whole lives. Okay. So here's sort of one of the fundamental examples in geometric group theory or coarse topology or lots of different things. I start with a torus. I take its universal cover, which is a plane. Okay. I realize that the plane could be expressed in, as a dot matrix printout of a lattice. Say this lattice might be the orbit of a point under the action of the fundamental group. Now, the top map is an arrow, it's the covering map, and that's, has detailed small scale topology. The relationship between the left-hand side and the right-hand side is, there's a discontinuous map from the left-hand side to the right-hand side. Okay. However, that map still doesn't distort very much in the large. Okay, so this is an example of what's called a coarse quasi-isometry. It was the observation of Milner and Schwarz that the universal cover of any compact space is coarsely equivalent to the fundamental group, remembering that the fundamental group is a finitely generated group and has a word metric. And different word metrics are quasi-isometric to each other. So this gives you some way of understanding, of throwing all compact objects, view them as just the equivalent to a point. It's forcing you to think big, but then you think about these kind of spaces, which are rather different. And now, here's sort of a first comment that you learn. Well, by thinking about on the, volume on the left becomes translated on the right to counting the number of lattice points inside of a ball of radius r. Now, a ball of radius r on the right might not be so round. It might be more elliptical or whatever. Right? I mean, that much stuff, gotta live with it. But you know that on the right-hand side, the length of things scales like r squared with r. So therefore, that tells you on the left-hand side, things do that. Now, of course, if I started with the plane, that would be no big deal. But I could start off with an arbitrary Riemannian manifold whose fundamental group is z squared. Okay, and the conclusion is that in the universal cover, in the small, of course, the volume of balls will be covered by the dimension of the manifold. So when you get to the large, it's covered by this kind of growth. And this is called the growth of the fundamental group. Okay, and it's sort of a basic fact that the growth of a finitely generated group is at most exponential, right? There's all this stuff that's sort of obvious from the combinatorial point of view. Okay, okay. Now there's also an isoparametric inequality, okay, which is a little easier to see on the left-hand side. If I take any closed curve on the left-hand side, okay, it bounds something. Whoops, it does bound something. It doesn't fill everything. Okay, right? It bounds something whose area is at least L squared. I mean, L squared is the best you can do for all things of length L. I mean, if I did something really wild, like non-rectifiable, it was bound, maybe bound something with finite area, okay, and that's much, much, much less. Okay, that happens sometimes. Okay, but the best you can do, and as you know, the circle is a great, beautiful thing. And on the right-hand side, you know, you then look for a similar notion. You look for closed curves among the lattice points, okay, and which, if you think about it, could be interpreted as words in the fundamental group which represent the trivial element. If you might as well make it be at the base point, at the origin. So then you really are having a word that represents the trivial element. And then the area represents something semantic, something syntactical. It's measuring how many relations do you use to see that that word is trivial. Okay, and now then you can go back and forth, and again you discover, oh, that for any manifold with fundamental group Z squared, if I ask for no homotopy curves of length L, they're going to need at most L squared to fill in. Okay, so again, this becomes a property that's common to all manifolds with this fundamental group, and it comes by, it comes by this coarse equivalence. Okay, so what I want to point out is that both of these notions are hidden in the homology of the loop space, if you look at it from the persistent homology point of view. Okay. Okay, so that's sort of goal number one. In other words, I want to say that persistent homology of loop spaces is something that we've been studying forever and ever and ever. Okay, right? That's not fair to say to Milner. It isn't that old. But anyway. Okay, so here's the first place. So here's my picture. So this is the free loop space. I don't know why I picked the free loop space rather than the loop space. It's a reflex that comes up when I think about the closed geodesic problem, but I'm not going to do that today. Okay, so you could, if you prefer, you could think about the loop space of X. So down here at the bottom, you just have the trivial loop. Okay, at the base point. Okay, what I'm going to do is look at log of the Lipschitz constant. Okay, so let's think about it. First, if you have any curve, you could reparameterize it by arc length. Okay, let's say we're looking at smooth loops. Okay, and doing that shortens the loop, so it doesn't seem so bad. So if you would be parameterizing by arc length, then the length is the same thing as the Lipschitz constant of the loop, up to factors of 2 pi. Okay, so, and now what happens if I'm looking at the loop space of a manifold or a space, let's say a manifold. Okay, if I have two different Riemannian metrics, right? I'm supposed to be looking at the norm of the differential when I ask for what the Lipschitz constant is, right? The size of that thing could be upper bounded by one constant and lower bounded by another one, right? If I have two different metrics, if I have G1 and G2 metrics on X, then, right, there's some, right, I mean, I could, right, and we're on a compact manifold or a compact space, right, I could always bound them above and below, in which case that the Lipschitz constant gets multiplicatively bounded, so I'm going to look at log of it to be additively bounded. Why? Because when we talk about the stability theorem, we usually talk about additive differences. Okay, so this is kind of a reasonable functional to look at. Okay, and now, say geodesics, by the way, are the critical points of this functional. Okay, so they are geometric objects. Okay, except that for this one, they're kind of geodesics that start from a point and end at a point and now come back at an angle. If I did the free loop space, it would be your conventional closed geodesics. Okay, I mean, but they're different variations. Okay, and now, of course, the homology of this, if I did the loop space, those are exactly the elements of the fundamental. Okay, and now the things of infinite length, right? That's the homology, right? So that's what I'm doing is I'm looking at this and I'm asking what are the bottoms of the infinite bars, right? And how high do they come up? Okay, so that's what the growth function is, right? It's measuring that spectrum. Okay, and what we're observing is that that's something about that spectrum, is pretty constant. Okay, and this is the fact that if something is quadratic, then it's quadratic. If something's exponential, it's exponential, stuff like that. Growth of groups is clearly in this picture. The other one is a little bit more complicated to see. So let's imagine that I'm over here, that I have a loop of this kind, right? I have some loop down here, which turns out, I wasn't aware of it. It takes a while for me to see that it's no homotopy. Okay, but what does this picture tell me? Well, this picture, right? I want to find it. If I had a no homotopy that I could follow around, okay. If I had a no homotopy that I could follow around, I could use that to build a disk that this curve bounds, right? So I could solve the isoperimetric inequality. So the diameter of the function space, in some sense, so I have to know how high it goes up, because as it goes higher, right, the rings are getting bigger and that's contributing more area. Okay, so there are two aspects that I need, right? I need to know the pH 0 bar, right, in order to bound this. And then in addition, I need to know something about the diameter of the function space, so to speak, right? If I have two things, right, that aren't, that are connected by through curves of length L, how complicated is that? Okay, well, that's a question about okay, so here's a lemma in graph theory. Okay, it's a stupid lemma, okay, but it's a lemma, so I'll say, okay, if I have a graph that has V vertices and it's connected, its diameter is at most V. Okay, right? I presume I don't have to. Okay, so in other words, so now what's the answer? So here I'm going to imagine this function space. I'm going to discretize it by taking little balls, right? We're going to be having things that are in the same component. Okay, right? I imagine that we've gone up over the hump and we've gone down to curves of length L again, right? And they're in the same component, right? So the question is, how many balls, right? So now we discretize, right? So in other words, I'm going to basically triangulate this space and have vertices. Any two vertices that are within the index that are close enough, right? If I have two loops in any space that are close enough, they together bound an annulus, right? So if I have those, right? So I could discretize here. That if my curves are close enough, then they're in this, then I connect, then I view them as being a vertex, and I connect two vertices that are close enough, right? So a centimeter apart. And now the question is, how many curves are there? Oh, well, that you could easily count, and that grows exponentially with the length of the curve. Okay, so the upshot of all of this is that the exponential of the length of a pH 0 bar bounds the isoperimetric function. Okay. Okay, right? Because there's the trivial lemma from graph theory tells you that once you know the level, the diameter is going to be at most exponential in that kind of thing, in the length in L. Okay, that turns out to be the estimate you get. It probably goes back to the 19th century, that estimate actually. But anyway, and so then it's just a question about what the height is. Okay, so in other words, this information is encoded in the persistent homology bars. And if I were giving a different talk, I would then explain, therefore, if the fundamental group had an unsolvable word problem, there would be infinitely many bars of arbitrarily long length, but still finite. And from that, you would deduce on any such Riemannian manifold, there would have to be infinitely many closed no homotopic geodesics. Okay. Right, so all of that is here, but for the point of view of today's talk, it's again motivation, right? pH 0 of any space with the loop space of any space with fundamental group I, right, carries this kind of information that seems important and classical, but once you put it in this framework, you immediately say, well, why should I only look at pH 0? Why might as well look at pH high? Why look just at things like K pi 1? Maybe I should look at other spaces and so on and so forth. It opens it up, and the real point is that lots of problems, well, from the pure point of view, lots of problems in topology, the way you start by them is you associate a function to your situation, and then you study the function by hook or by crook, okay? And then you'll really want to know things like about pH 0. So what can we say about other function spaces, right? So I just sort of explained what happens for K pi 1. So if you look at the beginnings of topology, again, focusing, say, on loop spaces, there was the classical work of Morse, right, where Morse theory was introduced. He wasn't interested actually in the finite dimensional case. He went straight to loops of Sn, and he deduced from that he computed the homology of it, and he deduced that for any Riemannian metric, there would be infinitely many geodesics connecting any pair of points and stuff like that. So Morse theory, so what's the point? So again, what you do is you look at the loop, you'll take log of the Lipschitz function, of the Lipschitz functional as being your functional. That seems to be a very good one. It has compact sublevel sets, okay, which is good for a lot of purposes. Okay, there are other functionals that might occur like problems, okay? And again, lengths of curves is very tied into the classical Morse theory. So for all of those, what happened, lots of times they were getting perfect Morse functions in some sense, either in the original sense of Morse or in a Morse spot sense. And in all of those cases, in those cases, you found one metric where this thing here has only infinite bars. And therefore, if you take any other metric, the argument I gave before said that log L differs by at most a bounded amount, right, depending on that constant C that relates to metric. And that therefore all the bars of all the homology groups simultaneously, all of those bars are going to be simultaneously of length less than C. Okay, so in some sense, so persistent homology gives you a little piece more than classical results, in that when you have infinite bars, there is at least one more piece of information, which is where does the bottom occur. But they're all infinite, so there's there are no other bars to be extracting information out of. Okay. Yeah, James is James. Okay, so there's like the James construction that gives a PL picture, a polyhedral picture of loops of the suspension of X. So for those spaces, again, you have a very, very good picture, but there are also no bar. This phenomenon that I mentioned about groups where their isoparametric functions are really big, forcing you to have lots and lots of long pH 0 intervals, right? Here there's, as far as one knows, for any function space where the target is simply connected, there's a dichotomy that bars are either of length less than some constant C, or they're infinite length, right? The possibility of a lot of finite dimensional bars, we don't know. I think that's a fascinating and important question. The H0 question is this: if I have two maps that are Lipschitz with a given Lipschitz constant, and they're homotopic, can I make them homotopic through maps that are CL Lipschitz? Okay, that's the H0 question. Okay, and Gromov speculated that was true in the 1970s. That's one of the speculations that we don't know the answer to at this point. Some of the speculations in those papers have turned out to be true. A couple of them have turned out to be false. We didn't have 20/20 foresight in that case, but it was still pretty amazing. Okay. But anyway, but that's sort of a great question, right? When you're taking it simply, right? The non-simply connected case, we see that geometric group theory tells us way at the bottom that there's a very, very rich structure, right? For a simply connected target, geometric group theory is not going to tell you anything much about the trivial group, unless you're a really deep geometric group theorist, okay? But the higher homology, Serre revolutionized calculating homology of loop spaces, and we don't know how Serre's work combines with geometry. Okay, there are I'm not saying it's impossible to squeeze estimates out of it. That was what Gromov did when he got that power of exponentials in the cobordism problem, was by squeezing Serre. At least that was what his proof sketch suggests. And I did that. Okay, but anyway. So we could ask about the growth. So here I'll just tell you what the answer to this 19th century question is. 19th century theorem is that, the volume, so to speak, right? In other words, you pick a small scale such that things that are sufficient, so that at that scale, the space of maps, has contractible balls, and that scale is, like in a manifold, it would be like around the scale of the injectivity rate. Okay, this isn't an insanely small scale. The volume at that scale is around exponential in the Lipschitz constant, but to the dimension of the domain. Okay, so that explains, by the way, for curves, it was exponential in L, and that's why we have growth of groups, which is the volume growth of this function space. That's at most exponential. Okay, but on the other hand, if the domain would be some other thing like a two-sphere, then the size of the function space, the volume of the function space, grows like exponential in L squared. And there are spaces like pi2 of a two torus wedge, a two-sphere, has x of L squared growth. Okay, if you try to, okay, so by the way, okay, I'm going to leave this as an exercise in visualization. In fact, I have almost no time at all left, right? I'm supposed to talk 35 minutes. So unless you're going to edit out, all of my bullshit remarks, I mean, I will have used up 35 minutes. So let me just say that there are nowadays lots of theorems pushing mainly on pH0, okay, I'm not going to explain applications. Yeah, so let me just say, firstly, just end with a few slogans, okay, rather than, explain. I hope I've whetted your impression about why this is a good subject. It looks like in some sense, there's a fractal structure on a small scale, okay? And I'll explain one theorem that maybe indicates that, okay? So what you should imagine is that, right, we have manifolds. So manifolds are boring in the small scale unless they're really non-diameter, right? And what you're really interested in is the large scale structure. So for example, supposing you were to take something, take your favorite fractal that, and take a homomorphism pi1 to z, and then you take its cover. So then that compact thing still will turn into something really, really non-compact. In the small scale, it looks like the old fractal, but its large scale geometry is governed by that z, right? Because you took a map to z and you took that cover, right? Miller's Fudge still holds. So that cover will look roughly like a line. So the large scale structure, it seems to be, is governed by rational homotopy. So spaces with simple rational homotopy types are the ones that are understood best. And the more complicated the rational homotopy type, the less we understand about it. And then, when you want to go beyond what, sort of predictions made by rational homotopy, then you have to use a different kind of argument for doing the small scale. Okay, and then basically what happens in the small scale is that, once your things are reasonably close, right, then you have to write some large pattern is determined. In the small scale, L versus 2L versus 3L just means that you were jiggling around a lot, right? So there's something common about going from L to 2L and 2L to 4L and so on and so forth. Okay, so if you want to, so here, just to give one example, okay, because I'm over time, of where this applies is the simplest case if all the homotopy groups of X are finite, right? So then there's no rational homotopy theory, it's like a point, right? So then all that you have is sort of this fractal nature. So what the basic theorem is is that firstly, all the persistent intervals are only, there's a uniform bound on the ones of finite. Okay, so for pH0, Steve Berry and I proved that many years ago. Jonathan and Block and I will write a paper explaining that. It's sort of even better than that. Okay, if over here you have, okay, I want to here look at the function space. I mean, and it looks, you know, it looks sort of crazy. So we know that there's a bound on the length of the intervals. Okay, but also there's a bound on the diameter. No matter how high the Lipschitz constant goes up, the diameter stays bounded. So from some coarse point of view, these function spaces just look like unions of infinite intervals, and those intervals happen to be the infinite pH0 intervals. We actually understand the large-scale geometry of these function spaces. Okay, there is no in all the other examples I know about, the geometry that I have in mind, you know, you take simplicial maps, and you know, and you either move through a homotopy in time, or you also allow subdivision. Okay, and that induces some kind of metric on the function space. It's okay, and with respect to that metric, typically the level L-ish kind of stuff has diameter that's log L, which is astounding. Okay, I want to point out this is, you know, this is better than 6 degrees of separation in America. This is something like something of size exponential in L to the D, having diameter about log L. Okay, so this is a really, really great small world phenomenon. And it's uncovered as you begin thinking about things like the persistent homology. Okay, so anyway, that's what's been keeping me out of trouble. So I'm open to questions.
Yeah, thanks, Shmuel, for your great talk. Let's all unmute and applaud. Are there questions?
Shmuel, I was hoping you could get me started on the exercise you gave with the torus wedge of the two sphere. So what happens for just the torus or the two sphere alone? And then how do I roughly speaking leverage the wedge sum structure?
Oh, okay. So here's the torus, there's the two sphere. Okay. First thing I'll do is I'll take the universal cover. Okay. Okay, so notice that in the universal cover, there are lots and lots and lots of two spheres. Okay, right? I'll choose a base point over here, and then I'll make that my preferred base point. Okay, and okay, so firstly, you see that pi2 of this space is z to the infinity. Okay, I mean, I could think of it as a module over, it may be more insightful to involve the fundamental group, and then it's actually z pi, where pi is the fundamental group, you know, but just as a group, it's z to the infinity. So, right, z to the n would make you think polynomial of degree n, right? Z to the infinity make you think that, oh, yeah, there's room for funny things to happen. So now here's a map from the torus. So if I'm going to take some, now here, I'm going to now map in the two sphere into this, and I'm going to, you know, flatten it. If I just flatten it to be a pancake into the plane, that would be insanely boring, uninteresting. I still, though, could get this thing here to cover a pancake of size L, and that's going to contain L squared balloons. Now, in each little checkerboard that over here is of size 1 over L by 1 over L, so you have to now checkerboard over the two sphere. For each checkerboard, there's sort of, there's sort of one two sphere that goes over there, and I could make a decision about, do I want to go over it, you know, like the little prince swallow, you know, with the snake swallowing the elephant, or do I choose not to? Okay, but if I do that, that gives me 2 to the L squared choices of maps, and they're all distinguished from each other by which cycle do they represent in the homology of the universal cover. Okay, so there, I've just given you, you know, that number of different homotopy classes. Okay, The reverse direction is some kind of counting argument that you get an exponential of L squared low upper bound for how many. This point of view actually, I saw the two inequalities come from such different places. One comes from just approximation theory, and just, how many functions are there if I pick scales and do the counting. But this one here, if my target would have been, say, if I would have had a surface of genus 2, right, then you'd think, oh, there are exponentially many possibilities. But then you would try to actually build the map of the two-sphere into these gadgets, and you discover that, no, you can't really make it, e to the L, right, which might have been one's first guess when you see this example. So it's an example worth staring at. But,
Thanks.
Yeah.
There are more questions? I have a question, Shmuel.
Yeah.
This was on page 5, I believe.
Okay, well,
Yeah.
tell me when I get to the page.
Yeah, right there, actually.
Okay.
Yeah, regarding bounding the isoparametric function.
Right.
This was just something that I think that I missed that you said out loud, which was the exponential lengths of the bars bounding the isoparametric function. Would you mind just saying?
Yeah. Oh, yeah. Oh, so. Okay. So if you start, okay, so let's say, so here you have L, and over here you have L prime. Okay. So, if you know where your L is, this thing, right? L prime is, where this interval ends. Okay. At that point, right, when that persistent interval ends, it means that the component that this, I might as well assume this one is a geodesic, right? Because everything goes down to a geodesic, right? So, right. So this thing was born. When it gets to time L prime, that's when it begins connecting up to some curve that's shorter than it, right? So you go up to this interval. Now, if I look at what's the diameter of the space of all curves of length L prime, where I'm willing to connect them through curves of length L prime times 1 plus epsilon, or something, right? Where that's related to that threshold of how close they are, that's going to be x of L prime. Okay, so if I know that there are, that the persistent intervals of finite length that are born at, at size L, right? Suppose I know that they're triple exponential. Okay, then, then I could guarantee that the isoparametric constant is at least doubly exponential. The isoparametric function is at least doubly exponential. Because otherwise, I'd go up to this level, and then and then there's at most another exponential's worth of, the diameter isn't that large to account for a very, very large isoparametric function. So if I know the isoparametric function is okay, anyway. I'm not saying that clearly. Should I try again? That if you know that you go up to this height, at this height, you know that the diameter is at most L prime, is at most x of L prime. So therefore, if you know persistent intervals, you get an upper bound on the isoparametric function. That will cost you one more exponential. If I know the persistent thing is like a triple exponential, then the isoparametric function has to be at least a double exponential. So if I know the isoparametric function is at least a double exponential, right? I'm not going to deduce things about the persistent, right? But I'll at least know that if I knew that the isoparametric example was doubly exponential, I'd actually learn that the persistent intervals would have to be singly exponential, and that in particular there'd be a lot of closed geodesics, and that those closed geodesics, right? Not only are they like, it's not like the boundary of it's not like the equator in the two-sphere where it's a closed geodesic, so you perturb it slightly into the upper hemisphere, and then it's shorter. Right, these are actually index 0 critical points, and they're not index 0 just detected by calculus based on small perturbations. They're index 0 detected by pH 0, and that if you would want to shorten them, you'd first have to increase them really to this, doubly exponential length, if that was, or singly exponential length, whatever the estimate you got on the persistent intervals.
I see.
So it's not a very, very tight connection between the, what's called the Dane function and the length of the persistent intervals. There's maybe a logarithm involved, and those, you lose information because, after all, that lemma from graph theory is a pretty trivial lemma. We haven't, I mean, right? It's a way of translating volume and diameter information, which is sort of an insane thing to do in general, right? In most settings, that doesn't make any sense, right? But here it does.
Yeah, thanks.
Shmuel, I was wondering how persistent homology is related to the proofs of the results you mentioned, Chambers, Manin, and so on. Are they interpretations that give different
those
proofs?
don't appear in the papers. Yeah, I would say that everything that almost everything I said today was revisionist history. Okay, right? I mean, right, like Miller and Starch and growth of groups and all of that stuff, right? That wasn't persistent homology. Persistent homology itself doesn't help so much. I think persistent homology could be used when you do the right, sticking it into the Serre spectral sequence and things like that. And it will, I think that such technology could be used to, in some problems, get you log, or exponent or powers of exponential kind of results. I mean, I think that would be the way one would likely formalize Romov's, remarks from the 70s. Where basically results that were asserted to be true in the past, previously by Serre and Ed Brown and so on and so forth, were shown to be, in some vague sense, quantitative, right? That there existed that. Okay. And in some sense, the stuff where you have a simply connected target. So let me just say that an area which I think is pretty right, is right for non-simply connected things. A certain chunk of geometric group theory could be reinterpreted this way. But I think that what happens for non-simply connected spaces, and looking at loops of them and things like that. I mean, that there's been almost no work done. In the simply connected case, I say there's an emerging picture. There's a lot we don't know. But there were some really unpredicted results even from a few years ago. And I think about work Bergnikov and Manin and now Larry Guth is also taking, proving some kind of really new and unexpected quantitative information that's rational homotopy, but not visible inside the minimal model. So it's sort of they're interesting discourse. Yeah, the thing with Jonathan Block, but once you begin thinking about persistent homology, it it suggests new questions that I think have their utility. I mean, Sullivan, when he introduced localization right after his thesis, he has this comment that's always stuck with me. He said, we introduced localization. So there he had this space G over PL, which at the prime 2 is more or less ions of the plane, and at the odd primes is more or less DO. And he said, we introduced this localization as a language, to express this thing. And if it were only a language, that would be enough. But in fact, having the thing as a space is so much better than a language, right? Because, then once you have it, you begin studying it and using it as a tool and so on and so forth. So I think that, I mean, I'm not recommending that everyone just translate things into Esperanto and say they're doing new math and that, but here I think it really is a convenient framework, for, so there's some foundational work, that still needs to be done, there's sort of, I mean, yeah. So the language of persistent homology, I think, just makes it very, very easy, much easier to express it. So there are theorems that Navitowski and I proved at the turn of the century or the millennium, depending on how you want to view it. And we talked about certain functionals having very deep local minima, and we didn't have a language. We just, we had to introduce it, and we talked about what we meant by the depth of the local minimum and so on and so forth. And it was because we didn't have the language at the time to say, oh, we're looking at the length of a pH0 bar. Okay, I mean, that, now it would, it just seems that paper was sort of, archaically written, so yeah. So I would say that, yeah, this is an advertisement, I think, of common philosophy as opposed to interfertilization of methods. The place where there is actually, I believe, a room for interfertilization of methods is on the problems of embedding theory because of the connections to dimension reduction. And I would say that the results on cobordism, people who know how cobordism is just proved in the work of Reine Thom, you take your Riemannian manifold, you embed it in the sphere, and you study something. So it turns out that in order to get, you can get Gromov's, you can reduce Gromov's power of exponentials to a polynomial whose degree grows like an exponential in the dimension, just using off-the-shelf ideas about Whitney embedding. But then you need really more refined ideas that are like related to the Johnson-Lindenstrauss lemma, but different, and and ultimately, such things would get you down to quadratic to get to the v part to the 1 plus epsilon. Manon and I use a technique that Gromov and Goof introduced that does re-embeddings as a multi-scale. It's a 2-scale process. So it seems to me that there's an example of something that's true for really all the quantitative stuff. And I don't know whether it has any value in data, right? But the idea would be, roughly speaking, to try to use Johnson-Lindenstrauss projection method in the large, and in the small scale, you use some kind of secondary method to not allow points that should be far apart to get,
Shmuel, let me just jump in and say that we're going to end the recording now. Everyone's welcome to either take a break or we can sort of continue offline. But yeah, thanks again for your talk.
Okay. Well, thank you for the